In this video, we'll be exploring some of the uses of vectors, specifically in physics with force vectors. So we're going to start with some definitions. The first word that we're going to learn is net force. So if you think back to other science classes and you kind of connect the dots, you might be able to think of what net force means. The net force is the sum of all forces. So you can kind of think about it like a fishing net that catches all of the fish. The net force is the sum of all those forces. If you go online and you look somewhere else, or if you end up taking physics, then you'll discover that we tend to write it as sigma F, where sigma is that mathematical symbol for the sum of all pieces of it. So this is how you might see it written as well if you're looking somewhere else. Equilibrium is another word you guys probably know from your science classes. If you think about it, it's balanced. So if something is in equilibrium, then it's balanced. In our case, think about it kind of like a seesaw. If you've got two people of equal weight on either side of the seesaw, it's balanced and it's in equilibrium. It's neither going up nor down. As soon as you put somebody heavier on one side or lighter on the other, it becomes unbalanced and it's no longer in equilibrium. And that's why it moves. So that person that makes it equilibrium creates that equilibrant force. It is a force that causes equilibrium. Force that causes equilibrium. Now I probably should make that look nicer, but I'm just not going to. Force that causes equilibrium. So these are the kind of the three words that we're going to be using. You need to know net force is the sum of all the forces. Equilibrium means that something is balanced, and equilibrant force is a force that causes equilibrium. So here's the first question that we're going to look at. We're supposed to find the component form of the net force in each situation. So if we think about our words, the net force just means the sum of all forces. Well, if we look here, I see three vectors. So a force is a vector. A force is defined as a push or a pull on an object, which means you are actually giving a direction to that push or pull. You're either pulling something towards you or pushing it away from you. You can also push hard or soft. Well, there's the magnitude and direction. Magnitude is how hard you push or pull, and direction is where you're pushing and pulling. So you can imagine that at this center, we've got some object that's being pulled in all of these directions. If we want to find the net force of this object, then we need to add all of these force vectors. Well, we've done tons of problems where we're adding and subtracting vectors. In this case, it's just purely adding. So there are a little bit of weird things that happen here, so I'm still going to go through it, but I encourage you to try and figure it out on your own, so go ahead and pause and try and figure it out on your own. So hopefully you've tried the problem, maybe you got stuck, but I'm going to go ahead and start giving you guys little hints. As you start to realize things, please pause it and try to figure it out. So I know in order to add vectors, I need to find the component form of each part. So I'm going to go ahead and give some color coding to this. I've got a yellow vector, a green vector, and a blue vector. So this is how I'm going to determine them. I need to find the component form of the yellow vector. I need to find the component form of the green vector, and I need to find the component form of the blue vector. Once I find all those component forms, I can add them together and find the component form of the net force. So that's your first little hint there. See if you can figure it out now. Now, what we're going to do is we're going to break these into triangles. Remember, every vector is a triangle in disguise. So if I bring this down here, you can tell this picture isn't super great that I made, but we've got a 72-degree angle right here. We also know that the magnitude of this vector is 15n. I said it before, but n stands for newtons. So 15 newtons. Well, now I've got the hypotenuse and the angle, so I can find the components on here. It points to the right and it points up, so I know both components are going to be positive. And I know in order to find those components, I've got opposite, so this is going to be 15 times the sine of 72. This is right triangle trig as we go through. This will give me the y component of my yellow vector. Conversely, down here, pointing to the right, this is my adjacent side. So it'll be 15 cosine of 72 degrees, and that will give me my x component. So now I just got to plug these into the calculator and figure out those values. So we get 4.635, and I'm going to 3 decimal places, but I'm making sure to save that number in my calculator. That way if I need to do something with it later, like add them up, then I can make sure to use that whole number. Rounded numbers give rounded answers. I want to make sure I never round until the very end. 6.5, so I'm just truncating, I'm just leaving it. It would be 658, which would mean I should put 266, but again, I'm just truncating. This is my work. At the very end, I'll make sure to round, but right now I'm just writing down numbers. So now we can do the same thing with this green vector here. Break it into a right triangle, where I discover I have 40 degrees here. Now something ends up being different about this vector. The yellow vector was all fine and good, nothing fancy there. But with the green vector, I'm pointing to the left and up, which means my x-coordinate is now negative and my y-coordinate is now positive. So this is something that we've done with vectors in previous videos and in previous problems, but right now we've got to be very careful because we know what we're given here is 40 degrees. So let's go ahead and use our right triangle trig again. Nothing fancy here, hypotenuse of 5, angle is 40, which means my opposite is my y component, and that will be 5 times the sine of 40 degrees. My x component, remember it's going to be to the left, so we've got a negative here, 5 times the cosine of 40 degrees this time. So I'm going to go ahead and plug that in and figure out what those numbers are. So I get, for my x component, negative 3.830, and for my y component, 3.213. And again, it should be 214, but I'm just writing down the numbers right now. I'll make sure to round at the very, very, very end. These are just placeholders. So here's where we're going to do the blue vector, which is going to be a little bit different. There's actually 2 ways to do this, and it doesn't matter which one you go with. It is totally up to you. If you're comfortable with right triangles, then what you probably want to do is draw your right triangle this way. Now, if you'll notice, this is different from how we've been doing it previously. The reason I'm doing it differently is because now we're given this angle as 13 degrees. So if you're uncomfortable with right triangles, then you may want to just continue to always go to the horizontal. Now, the downside to going to the horizontal here is this right triangle that's formed means that we're going to be using this angle. Well, I don't know what this angle is. I have to use this 13 degrees. If I want to draw my right triangle like this, then I have to figure out what this angle is. Now I'm going to leave that up to you. I'm comfortable with right triangles, and I know what's going on with these right triangles because we've been doing them for years. So I'm actually going to do it this way. This way is actually easier if you know your right triangles. So I'm going to go ahead and do it this way. Otherwise, you are more than welcome to draw it to the horizontal and do your math that way. Either one works. So let's continue with it this way. I've got my right triangle. What makes this weird, though, is now my opposite side is my x component. So to find my x component, it's the opposite side length. So now we've got 10 sine of 13 degrees. So that's what makes this weird. If you'll notice, the x component is always cosine if you go to the horizontal. But when you do it with the vertical, you've got the opposite side length for your x coordinate. So that's what's going to make this a little bit different, and that's where knowing your right triangle trig comes in handy. So y cosine of 13 degrees. So I'm going to go ahead and plug that. Oop, I forgot to tell about the positives and negatives. We are pointing to the right, so we're positive, and we're pointing down, so we're negative. Now I'm going to go ahead and get those values from my calculator. So for our x component, we're going to have a positive 2.249, and for our y, it'll be a negative 9.743. Again, I'm keeping all these decimals in my calculator. I'm just writing down the first 3 for my work, so I know which numbers to use. So at this point, it's just a plug and chug problem. I've found the components of my 3 vectors. I'm going to add them up to find that net force. So let's go ahead and punch all these numbers into the calculator and find our component form. So once we punch all of them in, we'll discover that our x component is going to be 3.055, and this time I'm going to round to that third decimal, 5055. I'm sorry, 3.055, and our y component is going to be 7.736. So here we found our component form for the net force. So what exactly does this mean? Well, what this means is I could actually get rid of all three of these forces. So instead of having three different people pull in these different directions, I could replace it with one person that's pointing 3.055 to the right and 7.736 up. So I could eliminate all of these vectors and replace it with one vector that does this, and it would be exactly the same. This is my F net, the net force that's going on there. So the net force is just the sum of all of those forces. And if I wanted to, I could find the magnitude and direction of this vector using the exact same ideas that we've been doing this whole unit. So there's how you add forces to create that net force. Now let's take a look at finding an equilibrant force. So if you'll notice in this problem, we're actually only given two forces. That's fine. I decided to give us two forces because it's a lot of the same work over, and I don't want to bog you guys down with doing the same thing over and over and over. So in this one, we're supposed to find the component form of the equilibrant force. So it turns out we start exactly the same way. In order to find the equilibrant force, we must first find the net force. So I encourage you guys to take a moment and try to find the net force, the sum of all the forces, F net. So practice what we did on that last problem and see if you can figure out the net force without me. So in order to find the net force, I have to first find the components of my individual vectors. So again, I'm going to color code them to make it a little bit easier for me. So we've got a yellow force and a green force. In order to solve this problem and find that net force, I need to find the component form of each of these vectors. So for this yellow one, I'm going to go ahead and turn it into a right triangle by going straight down to the horizontal. It now forms a right triangle, and I know my opposite is my y coordinate, So my y component is going to be the hypotenuse, 16, times the sine of 25. So Katoa tells me opposite deals with that sine. So now we can go ahead and find our x component, which is the adjacent, which tells me it's going to be cosine of 25 degrees. So I also have to be careful and make sure that I'm careful with my signs, the plus or minus. So I am pointing to the right, which means the x component is positive. I'm pointing down, so the y component is negative. Now I'm going to go ahead and find those values. So once we plug them into the calculator, 16 cosine of 25 gives me 14.500, again, decimal places. And then for the sine, 25 times 16, we get 6.761. And then again, rounding, we'll do that at the end. So let's go ahead and figure out, oh, I do not like that line. Let's go ahead and figure out the components of this green vector. So in this case, again, we could go to the right, which is what I would prefer to do, but I want to make sure I'm being fair to everyone, and we'll go ahead and do this problem. Oh, that's not my straight line tool. We'll go ahead and do this problem looking at this triangle. So this makes the x component cosine, but now I have to figure out this angle. So the trick to this is I know that each quadrant is 90 degrees. Well, if each quadrant is 90 degrees, and I know from here to here is 32, then I've just got to do 90 minus 32 to get this angle right here. So 90 minus 32 is going to give me 58. So I now know that this angle right here is 58 degrees. So now I can do all of my calculations using this 58 degrees instead of the 32. This is just one additional step that I'm not a huge fan of. I like to try and take as few steps as possible, and it turns out just drawing the triangle towards the vertical makes my life a little bit easier and faster. but you do you, whatever works for you works for me. So let's go ahead and find those components of my green vector. I know my x component is going to be negative since I'm going to the left. My y component is going to be negative since I'm going down. So my y component is the opposite side length. So the hypotenuse times the sine of, remember we're using 58 degrees. And then my x component is going to be my adjacent. That is 22 times the cosine of 58 degrees. So let's go ahead and plug that into the calculator and get our answer for the components. We get an x component of, remember negative because it's to the left, 11.658, and a y component of negative, because we're going down, 18.657. So if I want to find the net force of all of this, I've just got to add it up. Let's go ahead and add it up. We're going to get a positive, excuse me, I still have my line tool on. We're going to get a positive 2.84, and then now we're going to round 3. And then for our y component, we're going to get negative 25.41, and again, now we're going to round to 9. So here are our components for the net force. Remember, this is my net force, but that's not what the question's asking for. We want the equilibrant force. So this is my F net. I could replace both of these vectors with one vector that points to the right 2.8 and down 25. So this is what the net force is doing. This is how hard these two vectors are pulling together. Well, if I want to cancel these out, if I want the sum of all of these to be 0, I'm going to write this out. If I want the net force that we currently have plus some equilibrant force to be 0, well, that means that if I take, or if I solve for F equilibrium, it's negative F net. It is the reverse of F net. So instead of having this as my net force, if I change it, let me get a new color here. If I say my new equilibrant force, my F equilibrant, it's the reverse or the opposite of my current net force. That will cancel everything out and give me a net force of 0. The new net force, when I put this in, will equal 0. So this is my equilibrant in component form. It is the F net, but we take the opposite. Multiply everything by -1.